Okay, let's start with a wild thought. What if you could take two really, really dangerous things, combine them, and end up with something you sprinkle on your food every single day? Sounds like magic, right? Well, it's not magic, it's chemistry. And today, we're diving deep into the power of ionic bonds, this incredible force, this ultimate attraction that literally builds our world. So, picture this. You've got sodium, right? This metal is so reactive, it literally explodes if you drop it in water. No joke. Then you've got chlorine, this toxic gas, nasty stuff. You'd think putting them together would be a complete disaster. But instead, you get table salt, harmless, everyday sodium chloride. How is that even possible? It all comes down to this powerful process called chemical bonding. So to get what's going on, we have to kind of put ourselves in the shoes of an atom. You see, most atoms, like our friends sodium and chlorine, are just, well, they're not happy. They're restless. They've got all of this extra energy, they're unstable, and their one big goal in life is to find stability. It's this universal search for a calm, low-energy state that makes them interact and form bonds in the first place. And you know what? This quest for stability has a name, a very specific goal. It's called the octet rule. You can think of it as the ultimate state of zen for an atom. The dream is to have a completely full outer shell with 8 electrons, just like the noble gases, the super stable, super chill elements on the periodic table. This desire to get that perfect set of 8, well, that's the engine driving almost every chemical reaction out there. Okay, so that's the why. They want to be stable. But how do they actually pull it off? I mean, they can't just wish for it, right? They need a partner. They have to interact with other atoms. And when you've got a metal and a nonmetal, the way they do it is through one of the most clear-cut deals in all of chemistry, the ionic bond. Now, an ionic bond, it's not some friendly agreement where everyone shares nicely. Nope. Think of it more like a straightforward business transaction. It's all about one atom completely giving away an electron and another one snatching it up, a total give and take relationship. And in this deal, you've got two main players. On one side, you have the metals. They're the givers. They typically have just 1 or 2 electrons in their outer shell, and honestly, it's just easier for them to get rid of them to become stable. On the other side, the nonmetals. They're the takers. They are so close to having a full set, they're just missing 1 or 2 electrons and are desperate to grab them from anywhere they can. And here you can see that exact transfer happening. Check it out. The metal atom on the left just hands over its electron. Poof, it's gone. And because it lost a negative charge, an electron, it suddenly becomes positive. We call that a cation. Meanwhile, the nonmetal on the right gladly accepts that electron. It gains a negative charge and becomes what we call an anion. This whole process, turning 2 neutral atoms into 2 oppositely charged ions, that is the absolute heart and soul of ionic bonding. All right, let's circle back to where we started, our big mystery. It's time to dig into the salty story of how that crazy reactive sodium and that toxic chlorine gas come together to make something you put on your fries. So let's meet our starting players. We've got a neutral sodium atom just minding its own business, and a neutral chlorine atom doing the same. On the outside, everything looks fine, balanced. But deep down, we know the truth. They're both unstable, they're incomplete, and they are both looking for a way to change their situation. So let's really look at what's driving them. Sodium, the metal, has this one lonely electron in its outer shell. It just wants it gone. It's like an annoying house guest it can't wait to get rid of. Chlorine, the nonmetal, is the complete opposite. It has 7 valence electrons. It is so close to that perfect 8. It wants 1 more electron more than anything. I mean, you couldn't have set this up more perfectly if you tried. And here it is, the big moment. Sodium sees its chance and just donates its electron. And chlorine? It snatches it up instantly. In one single, super fast move, both atoms get exactly what they wanted. Both of them finally find that stability they've been craving. But this little exchange changes everything. By losing that negative electron, sodium is now left with a positive charge. It becomes the Na+ ion. And by gaining that electron, chlorine gets a negative charge, becoming the Cl- ion. They aren't neutral anymore. They're now charged particles, or ions. And this is the final, crucial piece of the puzzle. You've got a positive ion and a negative ion. And what's the #1 rule of magnets? And, well, physics. Opposites attract. And in chemistry, that attraction is ridiculously strong. This powerful electrical force that's now pulling the positive sodium and the negative chloride together, that is the ionic bond. It's like an invisible, super strong magnetic glue. So we've just created a brand new substance. Awesome. Now, what do we call this thing? Luckily for us, chemists came up with a really simple and logical system for naming these ionic compounds.
Okay, the rules are super simple. You're going to love this. First, you just say the name of the metal, the cation. So for us, that's just sodium. Easy. Then you take the nonmetal, the anion, and you just change the end of its name to "ide." So chlorine becomes chloride. You stick them together, and what do you get? Sodium chloride. That's it.
Let's try a few more, just to see how easy it is. You see Ki, that's potassium iodide. How about MgBr2, magnesium bromide, Al2O3, aluminum oxide? See the pattern? It's always the metal name first, then the nonmetal with that "ide" ending. Seriously, once you get this rule down, you can name thousands of these compounds. It's that straightforward. So we've been talking about what happens between just two little atoms. But what happens when you get millions, no, billions and billions of these bonds all forming at once? Let's zoom out and see how this tiny little attraction on the atomic level builds up to create the world that we can actually see and touch. Yeah, this incredibly strong bond has some major real-world consequences. Because the attraction between these positive and negative ions is so strong, it takes a ton of energy to pull them apart. And that's exactly why ionic compounds are solids at room temperature and have super high melting points. Just think about it. How much heat do you need to actually melt salt in your kitchen? A lot, right? That's the power of the ionic bond you're fighting against. And this is the beautiful result of all that attraction. It's not just a one-on-one thing. Nope. Each positive ion is pulling on a bunch of negative ions around it, and each negative ion is pulling on all the positive ions near it. This pattern just keeps repeating and repeating, building on itself, until you get this perfectly ordered, incredibly strong, three-dimensional structure. We call it a crystal lattice. It's amazing. You start with atomic chaos, and you end up with perfect, beautiful order. So there you have it. You start with two dangerous, unstable elements, and you end up with a stable, life-giving crystal. And it's all because of a simple, fundamental desire for 8 electrons. The ionic bond, it's not just some abstract idea in a textbook, right? It's the architect of so much of the world around us, from the salt on your table to the rocks and minerals deep in the earth. The real question is, now that you know the secret, where else are you going to start seeing this ultimate attraction at work?